to you the design of a microstrip patch antenna with a quattro wave impedance transformer 27 gigahertz. So this is just a tutorial on CST Micro Studio. Um, so we're going to do it in two main steps. First, you're going to start with this simple design of the patch antenna without any impedance transformer. So we only have the microstrip and the patch itself. And in order for it to resonate at 27 gigahertz, these are the following uh, parameters that we extract for the length and the width of and the height of the antenna. And the material that we're using is a Rogers 4003C, which has a permittivity of 3.55. And how do we actually extract these parameters here is by going to this website where you can input the frequency and the frequency and the dielectric constant, and it will give you the length and the width of the antenna. The height, I chose this height is because it's one of the heights that is used for PCB fabrication. Um, so let's try to design this antenna here using microwave CST Microwave Studio. So we're going we're going to have a new template here, and we go on microwave RF optical antennas, patch power slot. We're gonna choose the time domain because it's faster, even though it's a little less accurate than the frequency domain solver. And we can choose the dimensions as such. Set our working frequency. We're gonna choose from 0 to 50 degrees, and we're going to try to monitor the electric field, the magnetic field, and the far field at 27 gigahertz. So you can click on next and finish. So yeah, this will be how we set up the environment. First thing we're going to do is so define our substrate. So we can use go on modeling and then the brick, and then just define a brick here. So the x min, it will be the width of our substrate, which we're gonna call WS/2 minus, such that it's centered around the x-axis. We can do the same for x max. For y min, we're going to call this L underscore S. So it's going to be over 2. And then 2, so it's centered on the y axis. And Z min, we're going to keep it at 0. H max will be the height of our substrate. So we're going to keep it as H. And the material, as we said, it's Rogers 4003C. So you can try 4003. We're going to choose the glossy material here. We can load it and click on OK. And here to tell us what is the values for each of the parameters that we just defined. We can set the width of the substrate to be 7 millimeters, the length as well to be 7, and the height will be 0.508 as we defined earlier. So now we have our substrate here, okay? And let's now define the patch itself. Such. So for the patch, we have said, so we can call it patch. And x min will be, let's say it will be over 2. So the h min will be over the substrate, so it needs to be h, and the z max will be h plus the height, which we call tc of the conductor, and we're gonna choose a um, copper conductor. So you can click on OK and define all the missing parameters. So we have set for the width of the patch, it was, if we check again the values, it was 3.549. 3.549. The length of the patch is 2.598, and TC will just be 0.035. You can click on OK and you can see that you have the patch here. Um, we can also, let's change this name to substrate. Now let's define the ground of this patch. So you can also, we can call this ground, and it will have the same dimensions as the substrate. So we can use this. So it will be located at the bottom of the substrate. So all we need to change here is the um, z coordinates. And z min will be here minus Tc, because it's going to be the height of the conductor, the ground conductor, and z max will be 0. So you can preview it just to make sure it's correct. And you can see that we indeed have the ground layer. You can click on OK. And now, in order to excite this patch, we want a 50 ohm transmission line. And how do we make sure that we have 50 ohm a 50 ohm transmission line? We can use a macro that is on CST. If you go on Home, Macros, and calculate analytical line impedance, and for a thin microchip, because we're working on a microchip, so we want our frequency to be at 27 gigahertz, and the height of the substrate is 0.508. The dispersion is the permittivity is 3.55. We assume it's not a dispersive medium. So we can actually play with the width in order to get a 50 ohm impedance. So for example, if I click on calculate here, for a width of 2, we have 34. I found that a value of 1.145 would give us an impedance of about 50 ohm. Okay, so we can um, work with that. So we can exit and define the width of our transmission, the microstrip, which will be 1.145, and we can model it right here. So it will be trans, or we can equal it also feed. Let's call it feed, and it's going to be minus t over 2. Y mean is going to be, so we are in the end of the substrate, so it's going to be minus s over 2, and y max will be, sorry, to be L here, I'm sorry, and y max will be minus LP over 2. You can preview it. Sorry, yeah, we need to change this height of to H, and H plus TC. And if we preview it, now we get the correct dimensions for the patch antenna, for the microstrip, for the feed. Click on OK. So now our patch antenna for step one is ready. And how do we actually simulate this antenna? We need to define a port to calculate its S parameters. So you can click on F and double click on this face, the face of the feed. And then you can go on the macro, uh, solver, ports, calculate port extension coefficient, and you can construct directly the port from the picked face. Um, and then we will simulate the response of this antenna, but without a quarter wave transformer. I click on start simulation, and now we'll wait for the response. After the simulation is finished, we can go on 1D results and look at the S parameter response of this antenna, the S11, because we have only one port. And you can see that without any matching, so this antenna presents very poor matching along the frequency band. So I mean, a good matching would mean that the S parameter is at least, the S11 is at least um, under minus 10 dB. And it's not the case here. So we have mere at 27 gigahertz. If we look, if we, sorry, if we change position and put it at 27, you can see that we have a 3 point minus 3.4 dB, which is it's a very poor matching. So, and this is hence why we need to use a quarter wave impedance transformer. So how do we do so? To step two of the design. So now we can see that we've included a quarter wave impedance transformer, and we will derive its width and what it should be, what the impedance of what impedance it should be. So this is how we're gonna treat the problem. So um, we have our transmission line, the feed, which is at 50 ohm, and we consider the load to be the patch antenna, the patch itself. So we want to include in the middle a quarter wave impedance transformer of length lambda over 4 times the square root of the effective permittivity. And why effective? Because I mean, if you would take the permittivity of the material itself, it would be considered incorrect. And also, you need to make sure that the impedance, so the impedance Z naught will be equal to the square root of Zn times ZL. And you need to make sure that at the frequency that you're working at, Zin is a real number as well as ZL. So it should not have a reactive component. Okay, so you need to be sure that it does not have a reactive component such that this quarter wave impedance works. And how do you actually find ZL? So we have Zin, but how do you find ZL? And I will explain to you now how to do so. In order to calculate the impedance of the patch, what we need to do is do a process called de-embedding. So what is de-embedding? So we need to de-embed the port, which means that we need to bring this port 1 to the edge of the patch. Because now what we're calculating at this reference plane is the input impedance of the antenna itself. So the input impedance of the antenna, but we actually want to move um, this reference port to the edge of the patch. How do you do so? First, what we need to calculate is the distance between the the, uh, the input and the edge of the patch. So you can click on P, double click, and then another P again, double click, and you can get the distance here uh, between the input of the feed and the patch. And we need to move this first port to the edge of the patch. How do we do so? So you can go on post processing, then S parameter calculations, and then you de-embed the S parameter. So now, in order for the in, instead of the distance being 0, you can change it to 2.201. Then you click on OK, and here it will calculate the impedance and admittance matrices. So in order to make sure that the port has been correctly de-embedded, you can click here on ports and then port 1, and you can see now it's at the edge of the patch, and this will allow us to calculate what is ZL. Um, in order to find ZL, you can go on the 1D results and Z matrix and click on the Z11, and you can see that uh, at around, so normally you get this linear, uh, so it will be the magnitude of the impedance, but we are interested in the separation of the real and imaginary part to see the resonance of the antenna. And you can see that the antenna clearly resonates at around 27 gigahertz, as we can see here, where the reactive part of uh, of the where the reactive part of the impedance is nearly 0. So we can see that the real part is at 240 ohms approximately. So we can now say that this is our ZL. And now what we need to do is now calculate what would be the impedance of the quarter wave transformer. Can calculate the impedance, what should be the impedance of the quarter wave transformer, and find that it should be around 109.54 ohms. So we can do the same process for the quarter wave transformer to find its width. Um, we can go on the macro again and calculate analytical line impedance in microstrip 27, and we're going to place, so this is the parameters, and we want the phase shift to be around 90 degrees as well, because we are working with a quarter wave transformer. So for the width, we can choose it to be, for example, 0.23. I think it will give us, so let's decrease it a little bit. It's actually to increase the impedance, 0.25. Okay, we are nearly at our needed value, 24. I would say that is okay. Actually, we can use this value for the width of our quarter wave transformer. And for the phase shift, we need a 90-degree phase shift. So we're gonna input here 90, calculate, and this will be the length of our quarter wave transformer. Okay, so we can now input these parameters in here. So we can first I need to save these values for me to input. So we can exit, and let's define the width of the quarter wave transformer, and we said it was 0.224, and the length of the quarter wave transformer should be 1.7448. So these are the values for that we need to take into account. So what we need to do now is actually move the patch into the y direction, uh, so we can do transform, and you want to transform it plus the length of the quarter wave transform. So we can just put here um, this value, and if we preview it, you can see that it moves it to the end here. We can delete the current results. And now we can define what will be the quarter wave transformer. So we can define a brick. So we're gonna call this quarter wave transformer. The Y main will be minus QWT over W over 2. The Y main would be, um, so it needs to be at the edge here, which it was defined to be minus LP over 2. And then the Y max will be minus L underscore P over 2 plus KWT L over 2. And Z min will be H, Z max will be H plus TC. We can preview it. Let's see, I think there is a mistake. Sorry, it should need to be plus this. Yes, so it should be plus the length of the quarter wave transformer, and we can click OK. And now we can re-click on resimulate in order to check the S11 response, the new S11 response, to see if there's a match. So click on simulate. These are the new S parameters that we got from the simulation, and we can see that there's clearly a match. We can see around 27 gigahertz, where we are indeed below the minus 10 dB threshold. I mean, it's a very narrow band, in a very narrow band antenna, but I mean, because of the fact that the quarter wave transform is narrowband, there are many different techniques that we can use to make it more wideband, such as using a radial stub or a linear taper as well, um, to make it more wideband. And we can actually check as well the E-field response at 27 gigahertz of the antenna. We use contour to better visualize and use a dB scale, and we can animate it. So you can see that there's a good match if you see visually. I mean, there's not much reflected power at this 27 uh, at 27 gigahertz, and you can see the edge effects of the patch antenna that causes it to radiate. And we can also check the far field of our antenna at 27 gigahertz, where the gain is about 7.37 dBi. So thank you very much for watching this, and I hope it helped you.